Good morning. Sorry for the late start. I realized I didn't send you documents. And yes. So how did it go? We're reviewing my old videos. Did you guys get did you manage to do it? How much I don't know. I can't really go back because we don't have time, but you can let me know. How did you do in reviewing those videos? So towards the end, there was this set of questions for review that were discussed, and I did send them to you now. So you should have them in your email. And I also sent you the documents that were discussed, the risk and return. Good morning, Daviana, Angel, Tatiana. How's my microphone? So how did you do with your review of the pre-edited videos? Not edited, just pre-recorded. Oops, sorry. No comments? So maybe I can just recap what you should have seen. So it was a continuation of the statistics review. We ended off together. We talked about different kinds of, we talked about the standard deviation in detail because I explained that statistics is about averages and relative measures and nothing better than the standard deviation to show both of those themes, right? So you have the standard deviation, which is the square root of the variance. The variance is the average of the squared deviations from the mean, measuring how spread out data is. Okay. And then together we solved that, and then we solved this one. I showed you how to do this in Excel. And I did this because you're going to see this a lot. Okay, so you have data that is historical. Every observation has an equal significance or value, so your average is just a regular average and your standard deviation is a regular standard deviation. But when the data are presented like this is representative of a population. We use symbols that reflect parameters, mu and sigma, for mean and standard deviation, and I demonstrated how to calculate that with Excel. So I expect you to know how to do that. That's what we did before the weekend. And then I asked you to watch some videos that did some more statistics. In particular, you reviewed or you were introduced to scatter plots. And I pursued a discussion about looking at two variables at a time. And looking at two variables at a time, we look for a linear relationship or trend between those variables. And I talked about the correlation, the measure of the correlation coefficient. So if you didn't have a chance to watch those videos, please do. I talked about the correlation coefficient being between -1 and +1 and what you would expect. A perfect positive relationship would look like this, and it would be, R would be +1. A perfect negative relationship would look like this. So R is a measure of the direction and strength of the linear relationship between two quantitative variables. So direction is seen by if it's positive or negative. And strength is how close it fits to the line. So the stronger it is, the closer it is to 1. The stronger it is in the positive direction is closer to positive 1, and then in the negative direction, close to negative 1. When there's more scatter, it's closer or moves towards 0. The worse it is in scatter, away from the line, it's even closer to 0. This is an example of no relationship, where you could see, if anything, I put a flat line across this data, indicating a no trend. And then I differentiated that between an R of 0 with no relationship to this sort of relationship. It's not a linear relationship, but it's a curved relationship. It's still a relationship. And I suggested you shouldn't calculate R for this because it will be misleading. And then I spent some time on some examples using financial data. So then I bring it together, the statistics tools that you should have learned, together with some finance application. So I did that with these 2 sets of data. This is the data as historical, so every observation is equally likely, and thank you. Every observation is equally likely, and so we calculate this like this regular sample mean and the regular standard deviation, sample standard deviation, and then I talk about this is the covariance. If you remember, it looks like the variance, but I'm correlating X and Y. And then I explained what is correlation. It's just the standardized covariance. It returns or it turns this value, which for different variables, it's not exactly meaningful what a covariance is giving you because they have a different kind of spread. So the data could be, a variable X and a variable Y that you don't really understand the range of values or their covariance as a measure. So by standardizing, dividing by the 2 standard deviations, you convert it into an index that you can interpret because the index is between -1 and a 1. And then I just wrote it a couple of different ways, but these are all the same, essentially. Writing it this way is nice because it shows you that all we're doing is standardizing the values, or standardizing the values and converting this into an average of this multiple that becomes positive if the trend is the same with X as Y, and if it's opposite, the trend will be negative because of this multiplication. So multiplying a positive and a positive gives you a positive R if that happens repeatedly, and if when X is below its trend, Y is above the trend, you have a negative relationship. Or sorry, when X is above its mean, Y is below its mean, so they behave differently, then you would have a negative because you'd have a positive times a negative and contributing negatives to the R. So that's how, this is the variation of the formula that we focus on really. The most. And then I talked about calculating the slope and what it means. So is everybody okay with this data? Please tell me yes or no. And these results and the interpretation. say it's okay, so you want to keep reviewing? Well, you need to really understand this. So basically, what do you see here in the relationship here? How are those two variables related? I'm going to have to tell you to watch the videos because I can't go back. We don't have time. So make sure you watch. I put them in the description. I know that I linked them. I mentioned them. I guess I could give the links too. All right. So then this relationship is replicated here. Not replicated, but this relationship is explored between these variables, but I presented them in a different way as ex-ante data where they become like a distribution. It's a discrete distribution. It tells you the different states of the world, what can happen, and the chance of it happening. The most likely in this analysis is the normal state, and this was determined by using historical data, some information about expectations, some economic forecasts, and these numbers were derived. And then I say to you, well, you're going to do the same thing, but you're going to use the formulas, for the more general formulas, the formula for the weighted mean, the weighted standard deviation. As a result, you get the symbol mu because these are distributions. So this is the weighted mean, the weighted standard deviation, the weighted covariance, the weighted correlation. So again, this is the form of it that you're going to get more used to in this class. And this is the weighted beta. So anyway, watch those videos because I don't want to go back. I'm just recapping what you need. You really need to understand that well. I don't want to say too much because then you're going to think I explained it, and I didn't, because there's much to see in there. And then what I do is I give you the answers to solving for those, so you can check your work. Now in this one, you see that the relationship between them is double. When x is something, BCE is double. So what does that mean? If I was going to make a linear, if I was going to display a scatter plot of this data, I always make the market in finance, we always make the market X and the stock Y, okay? Because what we're trying to say is the market influences Y. And we have historical evidence for that. So we're relying on theory to be able to do that, right? Not just some data that we pulled out and we correlated. There's actually some rationale for what we're doing. So we put, otherwise, you shouldn't just say, oh, look at this trend, these data are correlated and one causes the other. But in this case, we because of the theory, we use X as the market. This is a measure of the strength of the economy, economic performance. And we always put the stock here. And you see a duplication. So how does that reflect here? It turns out that this is a a perfectly positive relationship in terms of correlation. And the fact that it's double reflects in the slope of this line. B will be 2. And I explain that to calculate the slope, we use the results of calculus that tell us when we optimize, we're saying we want the line that fits closest to all of the points. We are going to minimize the residual of being off that line. So we calculate the least squares minimum. So we minimize the sum of the squared residuals. And so that calculus results in this formula. So I go through explaining where that comes from, or reminding you, because you should have seen this before, and I refer to the mnemonic device to remember that as risk. So it's RSY over SX. You got to remember the general pattern, but it's SY on top and SX on the bottom. And why risk? Because B, the slope, is a measure of the sensitivity of the stock's returns to the market. When the market, based on the market performance, BCE performs 2 times as well. But what if the market performed poorly? If this relationship holds true beyond the range of values of the data, then when the market does poorly, BCE does 2 times worse. And that is why we say, it's sensitive, and remembering that it can be good, it can be bad. Doing something like this, though, outside of the range of data is not recommended. It's referred to as an extrapolation, and you shouldn't do it unless you have just reason to do it. But my point is that's the sensitivity. Like it's showing it can be a good thing, it can be a bad thing. But the worst case is, well, it's always doing better than the market. So it means that this can improve your return. And investing in BCE. All right, so there's not a lot of you here, but so watch those videos so you understand better what I'm talking about. So I make all the calculations, but in the end, the result is going to be this, and you can see it right away. So it turns out that the line, which I'm not so focused on, but the relationship would be a line that looks like this, and it should be, in statistics we use the prediction line with a hat on it rather than the line in mathematics, because this line should only be used in the range of the data. It shouldn't be used outside. So I put the hat on there to signify that. It's a statistical line, estimation line, prediction line. And then what I do is I have the solutions for the ex-ante data, which you should look at. And you should be comfortable with those formula. And solve all of these. You can, so what I've done here is, you can do this manually. If you just stick with the columns, I tried to line up these columns, but it doesn't look so good. So here, if I want to calculate the variance, it's the deviation from the mean squared. So I just take this column, minus the mean, this one, all the way down, and then take this column and put it here. So you're kind of replicating what Excel does, but manually if you were to write this on paper. And so use that concept of Excel to help you organize your paper, your solutions. It turns out that even though you can't see it directly because it's hard to visualize this with probability, it turns out that R is equal to 1 here as well, and B is equal to 2. So you go through the process to verify these. And I have all the solutions there. All right. So make sure you review that. Then what I did was I put on one page all the formula again using finance notation like your textbook or a finance book would. So these are all the same formulas, but rather than X, I'm putting R for return, return, return. And then what I do next with the notes is get into talking about where R comes from. How did these R's get derived? So it looks really long and really intimidating, but in fact, this is exactly the other formula. So I like to present the other formulas first to make you see that you've seen this before. I'm just making a finance application using a variable known as returns, but the same formula. I do that for historical data, and I do that for ex-ante data. So do I ever need to see these formula? I don't expect you to rewrite these formulas at all, but you should be able to read them and confident what you're looking at, knowing that this is the weighted standard deviation, weighted covariance, and this is the weighted correlation. You should feel all right about seeing that. So notice I'm going to go through this a little bit before I continue. So if I continue with the convention of putting the variable here for the market, I'm going to end up calling that now M as opposed to X, right? So this is RM, the market returns. And then here I'm going to put Y will be for the variable, the stock return or the company. And we use a notation I for that. So I for the stock is on Y, and M for the market is always on X. That's important for the notation, to feel comfortable with the notation. If I was to calculate correlation, so correlation with the sample result, so this is the formula for the setting of historical data. But now let's make a translation. Let's go from the correlation for historical data. Now let's do it for ex-ante. For ex-ante, I would write it as, I'm going to use the Greek letters, and this would be covariance. Are you with me? I don't know why I can't erase that. And then this would be the standard deviation of each of those. How's that? Comments? So this is historical data or ex post. This is for ex ante. And then I want to do it for, oh, I have to put, not, it's like that. That's the symbol that I used. Let me see what I did. Go back a bit. 6. I have to go back to the formula over here. So these are the symbols that I used for correlation. It's a Greek letter R for regression. So this is for ex post, this is for ex ante, and how would it look for finance data? It would be, or I could write this as XY here as well, because it's the correlation between X and Y. So for my case, it's going to be, I guess it's put in alphabetical order. So, and it doesn't matter if X comes first or Y comes first when calculating the correlation. Remember that, because the formula does the same thing to X as it does to Y. If you just look at this form of the formula, whatever you do to X, you're doing to Y the same. So it doesn't matter if I put Y first or X first, but it's a tendency in statistics to put things in alphabetical order. So that's why X comes first and Y. So when it comes to when X and Y are M and I put the I first, IM. And then this the covariance would look like IM, and the two standard deviations would be sigma I, sigma M. So this is for finance notation. Okay, so I'm just doing the translation. This is like Google Translate. Now I've done that for correlation. Let's do the same thing for the betas. I'll do it in the next column beside it. So for beta, or B, the slope, it's RSY over SX for ex post. For the slope, we use the beta symbol because it's Greek letters. We're treating it like it's a distribution and represents a population. So this is beta, this is rho, and then sigma y over sigma x. And I could put xy in there too, but I don't because it's obvious. And just to be fancy, however I do it here. So the beta of IM for finance the beta is also RSY over SX. In finance, the rho is, or the the correlation is rho IM. And then I have to put the y variable on the top, so that's I. So sigma I divided by the x variable, the horizontal one, in the denominator. So that's sigma m. So I just did a translation of the several documents. This is what I want you to arrive at, that you end up here. I could also write correlation, or I could also write beta differently because of correlation. If I substitute this expression into correlation, I can get a second formula for beta. So I'm going to substitute this in. And you'll see this will give sigma x y, so the covariance. Sigma y, I'm just recopying this thing, but then sigma x, sigma y. So these two cancel, and you have an expression that says that the beta, the slope, is the covariance per unit of variance. That's what the beta, or the slope, is picking up. The covariance per unit of variance. And finally, that would be here as well. I mean, I'm not going to do it up here, but you could do it for the ex post scenario as well. This is going to be plugging this in, sigma IM again, these cancel, so it's the covariance per unit, the covariance per unit of variance in the market returns. So, I have the feeling you didn't watch the videos because most of you left and you think you need to watch it, but I pretty much said what the most important things were. But if you feel comfortable, you know, you want to watch those again, or you want to watch those, that's fine with me. But we cannot delay, we must move on. So you have all the formulas, they're all there, they're all analogous to one another. So I'm just repeating the same thing with a different data set, different type of data set. And if you remember the UR case, what we're going to do next is introduce new information to reevaluate the UR case based on what our goal is to identify the right discount rate. So we're going to focus not on projecting the cash flows now. We're going to focus on determining the appropriate risk-adjusted rate of return that we should be using in our analysis. So that involves gathering a bunch of information, and I put it here in your case part 2. And I spent time talking about the origin of those return figures that we were just estimating correlation for. Where did they come from? And I had a discussion about them. So I spent an hour just reviewing what I said last time, or in the videos, but it was important. So all this, have a look at all of that. I talked about all of this. My goodness, I did all this. And I tied it all together. Then we do okay, then there's these questions you should start practicing. Start working on these as a review for your coming test. I believe I sent you the solutions. And that brings us to the next set of notes. So we notice in looking at different class of assets, the higher the risk, the higher the return. The fact is, with the higher risk, investors would only be incentivized to purchase those assets if there was a coincident higher return. So they only exist because of that, right? So I talk about, let's look at, this is now applying all that information about returns, and in this case where I use ex ante data, we calculate the mean and the standard deviation. And I think I stopped here. Is that correct? So I left that with you. I said to watch the first hour. I mean, if you went on, that's great. But you only needed to watch the first hour. So let's see if I start. Should I say the first hour or the first 40 minutes? I have to check. Okay, part 1. Okay, so we got as far as calculating the standard deviation. So I demonstrated how to do this. You should review this if you have questions. And this is our result. Now we're going to put it together. So this was calculating the mean and standard deviation for an asset where the information provided was ex ante. It meant that not only historical data was used to collate or present the data to you, also economic forecasts and prospective of the company were used to come up with this forecast of returns. So that leaves us with a mean of 15% and a standard deviation of almost the same, 14%. And I use the symbol mu, or I could use expected return for the mean. And I can use the symbol sigma for the standard deviation, and that's what I do. All right, so now what about, so that was like a review. All of that was a review of the review. So let's now look at, so this is new, what I'm going to talk about after an hour of this class has already passed. I'm going to look at two assets now, because in a portfolio doesn't consist on one asset, right? It consists of several. And we're going to focus on risky assets. And we're going to build towards what's known as Markowitz portfolio theory. So we begin with two assets. Again, presented in this discrete distribution that tells you about the possible outcomes with a lot of information incorporated to come up with this. So either you are we're going to be in a boom economy with 40% chance, or a bust economy, and this is more likely, 60% chance. And these are the two assets that I'm looking at. What do you see just looking at the numbers? What relationship do you see? So how should we look at this? Okay, so A is correlated with the market. When the market does poorly, A does poorly. When the market does well, the A does well. You see? Oh no, yeah, that's boom, that's bust. B, asset B, is negatively correlated with the market. When the market does well, B does poorly. When the market does poorly, B does well. So these then are negatively correlated assets because of their relationship in the different states. So what we're going to do first is calculate their individual measures of risk and return. The expected return is a measure of return, and the standard deviation is a measure of risk or volatility, creating uncertainty. So to get the expected return for A, this is an expected return, a weighted return. So we have to multiply these and then add them to the multiple of that. So this is the formula, but I prefer to do it in columns. I would do it like something like that. Anyway, you get 0.6 or 0.06 or 6%. And then the same thing for Y. Let's take the column here and multiply it by this column. And you'll get 7%. So individually, they have about the same return, though B gives a higher return. So you can also think about assets that correlate with the market and assets that are negatively correlated with the market. So we'll talk about that later too. Let's get the standard deviation first. So again, these are columns where this is my P, and they sum to 1. I never mentioned that before, but I have to sum to 1. And I need the deviation from the mean. So these are the deviations from the mean squared, pre-multiplied by the likelihood of either state of the world. This is the variance for A, this is the variance for B, and now I have to take the square root. The square root is 19.6 for A and 22% for B. So far, you should review that, make sure you can make those calculations. Use columns, use Excel if it helps you. It's not so hard when you just have 2 states of the world. You could probably do it on your own. I'll just do variance of A just to remind you I like to use columns. So I would take 0.4, 0.6 as my P, and then so remember, this is the deviation from the mean, and the mean would be the expected return. So again, these are columns. I take the returns for A, 0.3, negative 0.1, and I subtract, and then I just put the mean in here, 0.06, 0.06. Okay, so using the columns just makes it much easier. Multiply across, you can use storage to compute. So again, think of it like Excel. So what did we get? Very similar numbers again. So it looks like in summary, I have the summary information here. We found the expected return for A was 6% with a standard deviation of 19.6%. And the expected return for B is 7% with a standard deviation of 22%. And we see the higher return asset is also the higher risk asset. So which one do we pick? If we were to pick between the two, which one would you prefer? Depends who you are. We often assume that investors are risk averse, but we have to consider there's some investors who enjoy the risk. They're risk loving. What's a risk averse investor? A risk averse investor, when presented with 2 securities with comparable returns, will choose the lower risk security. Now here we're kind of stuck because they're comparable, but they're not the same returns. So it's hard to choose between them. So I'm going to introduce a calculation that will help you, or a statistic that will help you do that. Risk-loving investors, on the other hand, when presented with two securities with comparable returns, will choose the higher risk security. So let's first look at risk-averse investors. So with these numbers, I'm just recopying them. I'm going to talk about the coefficient of variation. The coefficient of variation takes the riskiness, which I will refer to, I'll use that to refer to the standard deviation. So it takes the riskiness and it divides by the expected return. So what I figured out is cost over benefit. You see, this is bad, this is good. This is what you dislike, this is what you like. So for every unit of what you like return, you get 3.27 units of risk. That's for A. For B, for each unit of thing that you like return, you get 3.14 units of risk. So which one gives you a better trade-off? If you're risk averse, you prefer B over A because this is a lower risk than that. If you're risk loving, you take A over B. And looking at this, as comparable type risk, they're not exactly the same. And they do have the trade-off of risk and return. So this is the best way to analyze them, using the coefficient of variation. Converting the values into risk per unit of benefit. Okay, so what's next? So we learned how to choose between assets, risky assets. What if, going back to our goal was to combine them in a portfolio. So we don't have to choose between them, we want to combine them. So mathematically, how do we do that? What are our expected return and the risk associated with combining two variables or two assets? So I say variables because this goes back to statistics again. How do we do this? Well, we know how to deal with we know how to calculate the weighted mean. We're going to expand that concept, though, to combining variables. We're going to create a new variable called P. So you see I'm using the R's now because we're in finance. We're deep in finance. So the return on A plus the return on B will make my return on the portfolio. But that's not how I add them together. I'm going to add them together thinking about, let's say I had $100 and I'm going to put $50 towards A and $50 towards B. So that's really 50% in A and 50% in B. So per dollar investment, I'm going to rewrite that. Oh, sorry. So this is my new variable I've created. The return to the portfolio per dollar invested where I'm going to call this XA the weight and this XB the weight. Is that okay? So just like ours tell us the return per dollar invested. So this is a new variable. I've created a new variable, and it consists of variables we have information on. So I know the mean and the standard deviation of A, and I know the mean and standard deviation of B. So I'm going to use that information to determine the mean and standard deviation of RP. I'm not going to go and do a deep dive analysis on this portfolio I created. I'm not going to create it and then gather data and see how I do in terms of returns. I'm going to use information I already have, because in probability or in statistics, there are rules of means and variances that apply to adding already known variables together. So as I go along, I'm going to review those rules. Maybe you don't remember learning it, or maybe you vaguely do. A review is in order. If you didn't learn it before, this will be your first time. Let me know if you need me to slow down. So everybody okay so far? So this is a new variable created by combining variables I already know about in a weighted. It's like a weighted average, because the trick here is XA plus XB is equal to 1. The weights will always sum to 1. So it's the case that, I'll put it in boxes like the theory, it is the case that the mean of a sum of variables is the sum of the means. Sum or difference. So if you're subtracting them, you would difference them, the means. So that's what this says. This just comes from writing E. I'm just recopying. Okay. So I'm recopying RP. I'm writing this, and this gives us this because of this rule. And I'll put it in a box. I'll put it in a yellow box. Oops, that didn't work. The mean of a sum or difference of variables is the sum of their means. So we're going to focus here. We know this, right? So we can calculate this one. So essentially it's just a weighted average. Oh, well, let's calculate it. So remember that, I'll move this away. Can't make it small enough. Oh yeah, I'll erase it. Doesn't fit. So this is going to be 0.5. RA was 0.6. And expected return of RA was 0.6. And this is 0.5. And the expected return of B, RB, is 0.7, I believe. Let's double check. Yeah. So the reason why I take some time to explain this is because there's going to be a lot of percentages floating around, and you got to be clear which one you're dealing with. It might be helpful if I write this one as a percent and the other one as a decimal. That might be helpful, I'm not sure. Put those like that. Another way to write this would be 6% plus 7% divided by 2. That would be the same thing. So the result is that this is 6.5%. All right, so we got the mean of the portfolio. Now let's get the standard deviation of the portfolio. That should be easy, right? No big deal. Let's see what that looks like. Ready? Variance. Aha. What is this? Oops, what is this? This is the variance of RP. Again, RP is equal to a weighted mean and we learned that the the expected return, or the mean of the sum of two random variables is the sum of the means. Now, I just leave the weight here outside because I should mention that the weight is known as a linear transformation. Oh, should I get into that? Well, basically, let's just say this. I'm going to make another note. I'm not going to make it a note. I'm going to make it another box to explain why so there's two things happening. The mean of the sum of variables is the sum of the mean, but I didn't explain why the XA, what we do with this XA thing. The fact is, whatever you do to the variable, you also do to the mean. If you multiply the variable, oh, sorry, that's not what I meant to write. If you multiply the variable by A, you also multiply the mean by A. So look, every value of the variable RA is being multiplied by 0.5. So then also you do the same thing to the mean, because the mean is just another value of the variable. Similarly, whatever you do to the variable, you also do to the mean. That's why you multiply here. So those two properties are rules, statistics rules that you should have learned. That I won't backtrack too much about, but those are the two principles. So you can understand that, or you can just copy what I'm doing. Follow along. So, okay, so those are the two properties. Now, what about variances? Those are the rules of means. What about the rules of variances? So, for the variance of a sum of variables, is it just so is it true So just like the means, is it true that the the variance of a sum of variables is just the sum of the variances? Is that true? How many of you think that's true? Or it's close? Okay, just say yes or no. So you think that's true? Who thinks that's true? Yes or no? So this would be like the mean. So over here I said the mean of the sum of variables is just the sum of the means, and it's like the weighted sum, because of this other part that I said whatever you do to the variable you also do to the mean. So the variable was weighted, both variables were weighted sums, so the weighted sum of means should also be true. No comment? Come on. Angel can't do the work for everybody. Anyone think this is true or false? True or false? True or false? You guys don't have much time to go back and review. It's already Tuesday. So you're going to do some review, but you got to learn with me as we go. So stick your neck out there and tell me, is this true or false? Skin in the game. Take a chance. So some people think it's true. Okay, it's fair to think it's true because it looks like what we just did before. Why wouldn't it be true, right? Keep going. Who else? Comment. Thank you, Danielle and Angel. There are the two mean. Okay, so it's not precisely true, but it's close. First of all, there's an issue with the weight. Remember what variance does. We talked about the variance, calculating standard deviation from the variance. Remember, we square all the values, right? So if we're going to take every value and multiply it by XA, when we deal with the variance, we're squaring all the values, including the XA times RA. So this actually gets squared. So I got to fix that. So the weight gets squared because of what variance does to a variable. And this is true in the special case Okay, so these are true only if A and B are uncorrelated. If there's a correlation or covariance right? Because correlation is the standardized covariance. If there's a covariance between A and B, there's an extra term. And I'm going to explain where that extra term comes from. So this is the extra term here. So first of all, is this okay with everybody? Why I squared this? Because whatever we do to the variable, we also do to the mean. Yes, but with the variance, we take the variable and multiply by XA. So in the variance, we actually square all the values before we do anything. We square the deviations from the mean. We also end up squaring the weights. So we have to square the weights when we use the variance term. So let me show you what in the world's going on here and all this. Okay, so let's see. I'm going to talk about combining assets in a portfolio with weights. And I'm going to have XA, RA. For now, I'm just going to use 2, and then we're going to talk about putting 3 together. And what I want to do is figure out the variance. So I have to think about the variability that's contributed by every variable. So what I'm going to do, I create a matrix and I consider all pairs of covariance. Covariance is only with 2, right? So I have to go pair by pair. So I begin with covariance of XA-RA with XA-RA. And then covariance of XA-RA with XB-RB. And then here, covariance of XB. So I use the matrix notation where I always put the row element first. Stick with me, even if you don't completely get it, you'll get something out of this. Promise. All right, so those are all considerations of covariability among the variables. This contributes a measure of variability for A and B, and B and B. Now, what is this? Let's have a look at it. Let's look at it in, I'm going to look at it in terms that are the simplest or the most memorable, because we've done it before a long time ago. I'm going to write that out. Like that. So that's what that is. That's the covariance of RA with RA, the pair itself. So how can I simplify this? I'm using the ex post formulas just because they're easier, because you're more familiar with them. So what can I do? I can factor out that common term and that common term, and I can bring those. That will be XA in the front here, an XA in the front here, right? In other words, there's my XA squared. I can bring it all the way in front. And that leaves notice when I use the ex post formula, I just use a bar here because the expected return is just the arithmetic average. Is everybody okay with this? So there's just two of these. So what is this formula then? Does anybody recognize it? Did I fix it, Angel? Okay, how's that? So what is this now? So what do you see here? This is XA square, and this is what? This is, come on. That's the variance of a finance formulas using R returns rather than X, okay? That is the finance expression. So this becomes XA squared sigma A squared. You already used it. Yeah, you've seen this before. So that's the variance. So what would this one be? So I'm jumping, you know, I'm jumping from ex ante to ex post formulas. I mean, ex post to ex ante. It's fine though. That's what it is. Okay, I'm going to give you guys 5 minutes to look at that and figure out what's going on. When I come back, we're going to finish this table and get back to the notes. Okay, how'd it go? What is this term? Anyone? Daniel? Angel? Diana? Danielle? No, I said Danielle already. Tatiana? Anyone? You don't see the pattern? The pattern is xb squared sigma b squared. This will be all the same as here, but I'll just have a b in the subscript, identifying the returns. And what about these? Are these the same? They are the same, because for covariance, it doesn't matter if I put the first variable here or here. I'll reverse them. It gives me the same result. And what is the result? This simplifies to become XA, XB, covariance RA, RB. Or, no, let me write it with the symbols. I'm going to use the ex ante symbols. So what's the symbol? Sigma AB. And that's the same here. This one is XA, XB, sigma AB. So we have 2. And so that demonstrates where the formula comes from, the formula on the previous page. So it says that the variance of XA, RA, X, so a portion of A and a portion of B asset returns that I will get for having the portfolio, the variance will be equal to so that variance of the sum is the squared weighted sum of the variances plus this extra term. This extra term is the covariance. Now, why is it XA, XB? Well, for the same reason. If I expanded this and I put XB, RB minus XB, RB bar here, you see I could factor out XA from there and XB from there, and they would be in the front. So that's where the formula comes from. And now let's look at the effect of this term on our result. You guys need to take a screenshot. So that's this. So if there is covariance, you have this extra term. If the returns are uncorrelated, then this would be 0 and you don't have this term. And here is just the expression for covariance that, like I said, it looks a little more harrowing when I write it in the ex ante form, but you should be comfortable to do it this way or this way. So you're going to get practice if you do the practice work. Okay, so what does this mean for our problem? We want to calculate the variance and then the standard deviation by taking the square root. So to get the variance using these values, do you need this information? What else do you need? That's not what I want you to. Oh my goodness, what happened now? Okay, so there's the data for that. What else do we need? We need the weights and the data, right? So we need this information. Actually, this would have been good. This is all I need. So taking that information again, work in columns. So I first take this column, then I go for this column. So I make the brackets. So I take the first column, negative 0.3, and then negative 0.1. And then I take this column, negative 0.2, and 0.25. And then I take the mean. The mean of A is 0.06. The mean of B is 0.07. So you would figure these out and then add them together. So what do you get? Turns out you get negative 0.0432. That's what you should get out of this exercise here. So what does it mean? What does it mean? It means, because it's a negative, it means A and B are negatively correlated. Now we knew that, but we actually have a metric. We actually have a measure of that. Although it's not really interpretable, like what does 0.0432 negative mean? We're not so keen about that, but we could actually, on the side, to understand it better, we could calculate the correlation if we wanted. We could say, what's the correlation RA, RB, which is going to be negative negative 0.0432 divided by the two standard deviations. So divided by the square root of each of these variances. I need more room. What does this do for me? This gives me a measure between -1 and 1 for interpreting the covariance. Now you don't have to do this, but I just want to check. What would it be? Because it's hard for me to interpret what 0.0432 is. That's correlation, right? To take the covariance and divide these. What do you get when you do that? Anybody do it? It turns out that they're perfectly negatively correlated. This ends up being -1. So these two variables, something else for you to verify, are perfectly negatively correlated. You can't see that with the number 0.0486, but that's what it is. That's like my R calculation. All right. So the effect of that on the variance is dramatic, with two perfectly correlated variables mixed together into a portfolio. The bad returns accompanied by good returns in the other asset offset each other so that the variability is muffled. It's just not so wild. Things are tampered down. So this is the variance. Look how small that is. Incredible. So that the standard deviation is 1.22%. Remember, when we calculate the standard deviation, we get to use the units again. Here we don't get to use units because the units are squared and that doesn't make sense. So look at that. Look at what we achieved by combining assets into a portfolio. This is an example of diversification. Diversification at its best. So I'm going to talk some more about that. Do you have any questions? So this is the strong effect of perfectly negatively correlated assets reducing the volatility. What was the original volatility? Remember that the standard deviation look at them individually were quite high. The steps of what? The steps of what? You can't do this in the calculator, Angel, because this is a weighted calculation. Unless you have the HP 10B, or I don't know how to use the TI 84, but you have to do this manually if you have the TI BA2 Plus. There is no formula in the TI BA2 Plus for this. This calculation? Or this one? The covariance or the correlation? Which one? Covariance or correlation? This one? Do you get a different answer? So why? All right, let's see. So if I was to do this in the calculator, I would do 0.5 squared times 0.0384. I could store that in 1 to avoid any problems, and then just do the next part, 0.5 squared plus 0.04 0.86 equals, and store that in 2, and then 2 times 0.5 times 0.5 times 0.0432 negative equals, and store that in 3, and then recall 1 plus recall 2 plus recall 3. Oh, yeah. And I get that result. So these are long results, long calculations, so you need a strategy for sure. And then the square root. And there you go. Okay. All right, so this is quite amazing, right? That we can go from 20% on individual stocks to 1% standard deviation holding two together. But they're two special stock, right? They have a particular relationship. They have negatively correlated, so one is a hedge against the other. One protects you against the adverse events associated with the other. What I'm talking about here on this page is, what if you had many assets, not just two? What would you do? When you see this symbol, I'm referring to use the matrix. Use the matrix. Again. And notice I have a weight in front, XA, XB, and we could have XC. We could have another. So this is for 2 assets. What about for 3? So this symbol is saying that you have to take 2 at a time and go through all the different possibilities and assets. So let's do 3 before we leave this for you to review. So I could have XA, RA, XB, RB, and XC, RC. So this is covariance XA-RA, comma, XA-RA. But I know what that is. We already discussed this. So I'm going to replace that with our known result. So this is going to be XA squared sigma A squared. And along the diagonal, I also know that this is this is going to be XB squared sigma B squared, and this is XC squared sigma C squared. And then it'll be, I'll put them in alphabetical order, AB and RA, RB, oops, sigma AB. And this one will be also the same, and there'll be 2 of them. Until you get the hang of this, there's going to be 2 of these. I'm going to use XA first, XC, and then sigma AC. But then the other one is over here, XA, XC, sigma AC. So there's 2 of those. And last but not least, we have XB, XC, sigma BC. And here XB, XC, sigma BC, and there are 2 of them. So our expression for the variance of XA RA plus XB RB plus XC RC is equal to sigma A squared with the weight squared that we already discussed. Why that is sigma B squared pre-multiplied by the weight squared and C squared. And then the pairs all the way down. So you could do this for n assets. It's a long expression. You need to know that it's possible to combine n up to, several assets into one portfolio. All right? So that's what that's talking about. It's saying take them in 2 pairs at a time, and this is basically the matrix. It's a symbol for that matrix. All right. So we appreciate diversification, and if we can identify assets that we could hold together that are negatively correlated, we can increase our risk, increase our return, and reduce our risk, both of the things that we like. So financial economists looked at this question and said, well, are there limits to diversification? And should we do diversification in a specific way? Is it really necessary to pick certain securities? So it's clear that holding them together gives you a much better return than holding them separate, like, sometimes holding A, sometimes holding B, and on average getting a return. It's better to hold them together in a portfolio consistently. So this means that combining assets A and B into portfolio P, we eliminate some risk, mainly due to the covariance term, where diversification is a strategy designed to reduce risk by spreading the portfolio across many investments. And it is true, you can diversify away some risk. That's known as the unsystematic or the asset-specific risk that is unique. However, you can't diversify away all risk. In general, if you were to take no specific analysis of potential assets, if you were just to randomly choose assets, just put them their name on slips of paper and throw them in a hat, or randomly select with a random generator in Excel, you could pick about 25, and it turns out that that's the best you can do on average in eliminating risk this way, just purely from the diversification effect. So this is what actually was done in experimental setting. So information on all assets was obtained, available assets, and they were randomly selected several times with a different sample size each time. So several times of selecting one at a time. On average, the standard deviation of one asset in a portfolio of one was 49.2%. It's quite high. And they did it for other kinds of sets, but for 10 assets at a time, they selected randomly 10 at a time and calculated the mean and standard deviation. Then they did it again, randomly selected 10, calculated the mean and standard deviation, and then did it again. So they did it on repeated samples and averaged the results and found out that the average standard deviation of 10 assets combined into a portfolio had a standard deviation of 23.9 on average. Then they did it for 11 and 12, and they did it for 20. After 25, like combining 30 or 40 or 50 or even 1,000 assets, didn't succeed in lowering the average standard deviation across those sampled portfolios. So the conclusion from this study was that, look, if you're not even trying to pick them properly, this is the best you can do. If you start trying, maybe you could lower it some, but the idea is, it's not the number that's going to help you. It's selecting them in a specific way. And the thing that you have to care about, it turns out, is how those assets interact or are correlated with market risk. And that's known as a systematic risk or non-diversifiable risk. So what we care about what we end up assuming in the theory is that anyone can pick as many assets as they want. There's no additional cost to having more assets contributed into a portfolio. But we do have to think about carefully is how we pick them in their relationship to market returns, because there is systematic risk across all assets introduced by the market volatility. So where total risk is diversifiable risk plus market risk, and we assume diversification is costless, so that diversifiable or non-systematic risk is irrelevant, investors should only care about non-diversifiable or systematic market risk. And market risk we already know, so this is coming full circle for all our invested time in statistics. Market risk is measured by the sensitivity of market changes. Well, a stock's sensitivity to market changes. That's measured by the beta. So that's just the slope. Remember? The slope of what? The slope of the linear relationship between the market returns and a particular stock's return. So I used two here. Two possible scenarios and plot those. I say they're equally likely outcomes. I should mention that. They're equally likely. And because there's only two, a scatter plot of 2 points is just a line. So here are the points, and a measure of sensitivity would be the slope between those points. This is just change in y over change in x. So the change in y from one point to the other right? 26 minus minus 4. And then going in the same direction, the change in x would be 18 minus 6. And you get positive 2.5. I'll just call it 0.1 and 0.2. So what does it mean? We interpret this as a slope. We use the Greek letter because we're using Greek letters in finance, but it's also trying to insinuate that we have the population data, right? Because this was set up as though it was a ex ante, even though the weights aren't there. It's 50-50 assume. So what does it mean? When I take a slope, I put it over 1, and I say, for 1 unit change, in the market index, you see 2.5 unit changes in the BC returns. And for 1 unit change, 1 unit positive change, you see a positive change in BCE returns. For a negative change, you see negative change in the BCE returns. So this reflects the sensitivity of the returns to BCE stock with changes in the market. So it's very sensitive, 2.5. Any comments? So you can find the slope this way. You need to remember that the beta can also be found as the correlation. As the correlation. I have to do it this way. So in general, the slope is found as RSY over SX, but we're doing it now in a specific way with a specific Y and a specific X. So the beta where the Y is always the market returns and the X is, the Y is always the stock returns, and the, what did I just say? The Y is always the stock returns and the X is the market return. Notice I always put the market here and the stock here. Then this is going to be always like that. And keep in mind that correlation is really the covariance. Then the other term to write is this way. So those are both measures of beta. So if the correlation is negative, the slope is negative. If the covariance is negative, the slope is negative. Right? So that's the point here. So where we think of the market portfolio as the portfolio of all assets in the economy, we use this broad stock market index such as the S&P 500 to represent the market. And for the beta is a sensitivity of stocks returns to the returns on a market portfolio. And we end up with these formula. And I show you these two versions, and this one comes from using this substitution, where this is just the standardized covariance. So that's why we did the statistics review, because I'm going to use all these results that we discussed. So that brings us to portfolio theory. How many of you learned portfolio theory in the past? Okay, Daviana has seen it. Nobody else? Okay, so see these formulas, you got to be comfortable with this stuff because I'm going to be flashing them in front of you. All right, so the discussion is going to be regarding, well, we only have 20 minutes, not even 15 minutes left. So let me skip this for now, and I'll talk about that later. Where is this going to bring us? No, I'm going to go through it consistently. Let's stick with this. Let's see how far I get. So we can reduce standard deviation of a portfolio by combining stocks. And the covariance or the correlation coefficient is what makes it possible. Where this formula, we are familiar with this formula of the standard deviation. This is the variance, and that's the square root, which makes it the standard deviation. Is that, and we can write it this way, or if we have information on the correlation, we can write it this way. These are the same formula. I've just substituted this for the correlation because, like I say, we often understand the correlation, and this is the number as a result that we mentioned, not this one so much. So this is an example to demonstrate theoretically what we're looking at, this trade-off between assets that we combine. We're going to look at two at a time, and then we're going to go to the n asset case. Looking at it two at a time, I'm going to talk about Y and Z. When you look at these two assets, which is the riskier asset? Which has the greater volatility? It's going to be asset Y. And as we expect, the riskier asset is accompanied by the higher return. Daviana, what's the regression formula? What we're doing? Yeah, I'm going to continue. All right, so the riskier one is Y, but it also has the higher return. So if I create a trade-off diagram here, don't worry about all the numbers and all the lines right now. Focus right now on the fact that Y is here because it's the higher risk, higher return asset. Okay? So those are both the mean and standard deviation if you go back here. Mean and standard deviation. So it's plotted as up here. And Z is the lower risk, lower return asset. So on the axis, I have return, and risk. And Z is down here because it's lower risk and lower return. So it's low, and Y is high risk, high return. It's high. And I want to consider combining those two, just two I'm thinking about right now. And this graph will show the results of combining them in terms of what is the portfolio's because that's what it has here, P and P. What is the portfolio of the combined assets? What is its risk and return? Like we can look at some key points like this one here, and what are all these lines here? So what I've done is I've generated all possible outcomes if correlation is something in particular, the correlation between the variables. So what I did here, I'll say that I'm going to be giving you, we can determine this one, oops. Where all this information is given, so all that information is given. What's not given are the weights. How to combine. What is the best weight? We're going to figure out what the weights do in general, and then we're going to choose among them. So notice I made an expression here for the formula of the standard deviation of a portfolio combining Y and Z assets in terms of their returns. And the unknowns are Y and Z, where remembering that the weights sum to 1. So what is the ideal weight? Well, it depends on what I'm looking for. Here are the bits of information given. I give you the different correlations, and these are extremes. And I also gave you information on the standard deviation. So this is the given part. And then this is also given part. And I go with the extreme cases. What if they're perfectly negatively correlated? What if they're perfectly positively correlated? And what if they're not correlated at all? These are the different portfolios I'm going to consider, different combinations of the assets, their expected return, and their standard deviation. So I'm going to take this column, so imagine that you have the assets perfectly negatively correlated, just like the example that we discussed. If you combine, remember, Y is the riskier one, right? So if you have more of the risky one and less of the not so risky one, so more of the relatively risky one, this is going to have a higher level of risk than any of them below. So this row has more of Y in it. The riskier asset. And this row is even Y and Z. And this one has more Z. And you see that information here. Portfolio 3, more Z. Portfolio 2, the same. Portfolio 1, more Y. So the one with the more risky asset has higher volatility across the board. The one with the lower risk asset has a lower volatility. But up here, I'm showing that the highest return is associated with the higher risk asset. So what do we do? What do we choose? I look at 3 different states as extremes to see give you an idea of, in general, how we would approach this. If they're perfectly negatively correlated, the possibilities are along this line and this. These are the possible combinations of the two assets. And I only calculated a few points and I plotted them here. But you get a smooth line like this. So for instance, when you put more Y in there, the expected return is 18.6, but the standard deviation is 7.38. So with more Y, 18.6, and you see this is going to be 7.38 here. So that's 75% Y with correlation equals -1. That's the combination of risk and return you get. So I'm going to pick up here tomorrow. We're going to talk more about this. You can sleep on it, and we'll talk about this. And then I'm going to tie that to the capital asset pricing model. And we're going to use the capital asset pricing model to estimate required rates of return. So that's what we're going to do tomorrow. I'm going to send you some more materials that you'll need and more exercises for practice. Just looking at it. We can do this for tomorrow. And then we should be on to the new material. So I'll send you a bunch of exercises today. Any questions? So rewatch those videos I sent. You have to be very strong with statistics to get through this. And Daviana, you have to clarify your question about the regression. Is this like a regression? Well, you'll see. It's, if I answer your question, we're plotting those lines in different states of the world, considering combinations of those assets into a portfolio. Some with more of the risky asset and other, or one with the more risky asset, one with the less risky, and one with equal amounts of the assets. And we will establish the options and talk about how to choose among the options. We do not get to choose the correlation. That is just a result of the relationship between the given variables. When I say given, that we don't get to control that. We don't choose that. What we do get to choose is where we want to invest. All right, so I'm going to say good night, good afternoon. And hopefully we'll finish this and get on to review. And I can get on to the next unit before Thursday. So no breaks. If you fell behind because of yesterday, make sure you spend double the time today watching those videos and understanding, remembering statistics. Okay, bye.